about the closure Common Lisp distribution and a CBCL compiler for the Lisp. Then I did some kind of update, and also it's running. So I completed the installation via installing SCL2 using some apt installer from the Ubuntu distribution, and it's nowadays distributed via 8.4 version, but the latest version is 8.5. So if you would like to discover the latest theorem improver ACL2, I would like to recommend you to use Docker image, which you can use with the following command. Using an ACL2 sedan, it is deprecated. It's an Eclipse IDE plugin, which allows you to verify your software and hardware inside Eclipse IDE via graphical user interface. Mainly, ACL2 uses a REPL read evaluation loop, which you do some kind terminal or console things and copy and paste the actual code from file, or you can just do it manually. I'll use a theorem improver, which is famous by company on the slide like Intel, AMD, IBM, ARM, etc. They use SCL2 and many other things. Arithmetic progression from 1 to n. So at the beginning you have to define the precondition. The n should be above 1, because if it's below 1 it will not work correctly, because we want to get some result from this. On each point A, B and C we have some kind of logical conditions which are called a specification variant. So how can we formulate a loop invariant? We just check the variables inside the loop and try to decide for every step of the loop. So for example, I minus 1, I divided by 2, and I less than n plus 1 stays forever for this part of the program. Then we have to, which I recommend just read a flying tour. And then we are going to discuss how can we actually prove something inside the SCL2. I just copied and paste some ISAR example, which is famous from the Isabelle Hall theorem improver, in the name of the theorem. Then we have to define the formula, the statement of the formula. I want to note that SCL2 is a first order logic theorem improver, rather than, for example, in Isabelle and Coq you can have a higher order logic functions with infinitely many types of inclusions for the quantifiers. In SCL2 you just have to formulate your formula with exact values. So for example, if you have just integer type, you can formulate your quantifiers for integers, not just some dependent types and other things. Then you have formulate a proof. Proof is always a list in Lisp. Because ACL2 it's a Common Lisp subset, you have to write your proof via Lisp syntax. Proof it's a list, and then you have to do some disables. You just know that something is not going to be happen here inside this proof. For those kind of reasons you have some kind of commands which not allow to the automatic theorem improver use those rules, and you are able to specify which rules are able to implement it to formally prove this formula. After the last parenthesis it goes to the ACL2 theorem improvers, and this theorem improver automatically try to check this proof using the proof tactics and those some kind of properties. and then certify this statement that that's true or that's false. If it's false, you have to redo your re-implement your proof. This is the way how you are proving your theorem. Okay, so here, as you can see, we have some kind of CPU architecture. There are a lot of digital blocks like control unit, which is just a digital function with zeros and ones. We have some kind of memory, we have some secondary memory, we have some periphery devices, ALU, arithmetic logic units, registers, etc. Just standard stuff, and all of this you can simulate, embed inside the ACL2 and formally verify some statements about this. It's a pretty common technique for companies like Centaur and other companies who are developing the CPU, and they're trying to avoid bugs inside their hardware, because if they do this, it leads to some kind of huge disasters. What is a chip? A chip is abstract finite automator in the mathematical sense. As you can see on the left hand side, you have some kind of function for changing the states. It's a lag operator or registers. It's a function for outputs, and you do this in a clock cycle manner behavior. So those equations can describe you every digital device in your working experience. So at the beginning you have a 0 state, 1. Another equation defines all possible changing of the inner state of the chip, and the third equation defines to you all outputs of this device. So this is a way how we can divide those chips, and inside the function P and C you can use particular function like XOR, AND, OR, negative, etc. Just to implement this chip inside your hardware. We have programming frameworks like SCL2 hardware books, the Verilog toolkit, x86 ISA, instruction subset for assembler model, System C, the Cadence just performance verification platform, Vivado, SAIL, it's a famous by the Isabelle theorem prover. It allows you to formally verify RISC-V open source hardware architectures. TLA class, it's a very commonly used model checker. It's famous by the engineers, and mostly it uses for distributed systems, concurrent systems, and some kind of abstract modeling for the software. Another VHDL and Verilog infrastructure you can find via those links. This is the tool how you can visualize examples in Verilog. Example layout, load example code, ladder. Yep. As you can see a circuit. So it's a Verilog implementation for some kind of digital device. Okay. Verilog does not give an access to trace or place components on a silicon. It is hardware description language. So after execution at Verilog, there are some synthesizers who do actual work for you. For example, if you do some description for this statement, the synthesizer goes on and create for you this picture. So this is done automatically, and the user does not access for actual designing small parts of this inside the Verilog. But you can just plug in your components using some kind of logic and dot notation. We will discuss this later. And how does this work? This is for example, we are trying in some kinds of way to solve the chip size estimation. Imagine that we have the size of an input, and as we know, there are to place input and output sockets. then we are going to do some auto placement of components. We can use some Kernighan-Lin algorithm and Gordian algorithm for optimal component placements. And also we have to do some trace routing, for example, for copper rows inside the silicon. We are developing algorithms to automatically create optimal copper traces between components based on our electrical properties and the exact placement. There is a gamma algorithm on graph which has the following statement. The graph G is planar if and only if the gamma algorithm places it on the plane. And if it's not, we have a technique in graph theory which can allow you to split into the layers. And so this topic is implemented inside the popular software, and usually user does not have any idea what's going on inside the synthesizer. So let's focus on the Verilog. We have to define specification for the CPU inside the Verilog, model CPU blocks in SL2, write properties and assertions, performance verification, and do some documentation and review, which is called xdoc. There are examples of CPU blocks: arithmetic logic unit, control unit, instruction decoder, register files, cache memory, floating point unit, pipelines. All of them are verifiable by ACL2 and another software. If you have, I would like to provide you some practice with this topic. If you would like to do some Verilog coding and formally verify all of those sources, I would like to give you some kind of problems which you can do on your own pace. And for example, you can create a bus decoder plus first in first output model with instruction decoder and average calculation mode. You can do some inside the Verilog, formally verify inside the ACL2, do some encryption modulation, which is a topic of our discussion. And if you get stuck, please follow this link or find me on LinkedIn and ask me a question. Even it's not fully implemented on the GitHub, I'm going to provide all of the information on those problems. There are just 10 problems: division by a constant for module's parameter, count the number of individual bits in the input vector, return the result as a double number, which is quite common in your practice. But for example, the gray code implementation, generating gray code sequence, it's not quite useful, but I recommend you to start from UART driver or I2C driver verification, which is just a commonly used part or module for the hardware. So how can we do verification inside the SL2? Imagine we just implemented some Verilog file, it translated in some kind of silicon, and with those files we have to embed inside our theorem prover. So we do some symbolic simulations, do some manipulations with the actual language constructions, construct a tree, visualize them, and do some hardware output as a binary decision tree. And we have some kind of simulation specifications from the ACL2 part in the described and the logical sense. And we can try to, is it correct that the output binary decision tree is the same as the binary decision tree for the Verilog? This way, this is the way how we can find bugs inside our Verilog designs. There are different techniques, but we would like to focus on the VL and SV implementation of this scheme. Here's a Feistel block ciphers. Feistel block cipher is a symmetric structure used in the construction of block ciphers. A large number of block ciphers use this scheme, including US data encryption standard, the Soviet Russian Ghost, and the most recent encryption standards is called a blowfish and twofish ciphers. So it's a very interesting example, and let's check this video.
For this one, we're going to talk about Feistel networks. I love Feistel networks. They're brilliant. They're one of those things in cryptography where you just think, wow, that's very clever. That's really elegant. And it's not even that complicated, and yet you just think that's great. The Feistel network was designed roughly around the 70s when Horst Feistel, who worked for IBM, who was a German physicist, with the NSA, he helped develop the data encryption standard DES. Right? Now DES was, as we know from a previous video, replaced by AES eventually, mostly because of its short key length. But DES, the structure of DES is something called a Feistel cipher. Right, or a Feistel network. And there are a few of these around. Twofish, for example, is a Feistel cipher. Feistel ciphers see use in padding, right, which is going to be some kind of pseudo-random function like a hash or an encryption round or something like this. We're going to take it out here, we're going to XOR it with the left, and then we're going to bring the left down, and we're going to bring the right down here, and this is your next block.
So when you say left, you mean the left-hand side of that block on the right-hand side? Did it have to be exactly half and half?
Ah, very good question. So in this case, yes, but in general, no. You have unbalanced Feistel ciphers where the left and the right are different sizes. For this demonstration, they're going to be the same size. As near as I can draw it, I'm not very good at drawing. So the next round is exactly the same. We take whatever this new right is, we bring it around, we go through F, we XOR it with the left, and we come down here like this, and so on. Right? And you can repeat this process as many times as you like, for however many rounds. And then at the very end, after the last round, you flip the output, like this. Now, this is a structure for encryption, in the sense that you can put in any F here, and you sort of build yourself a cipher. Now this F obviously needs to be somewhat reasonable, but what's so incredibly clever about this encryption algorithm is how you decrypt it. To decrypt using the same Feistel cipher, you encrypt by putting your block in here, it goes through here, it goes through here, it goes through here, and it goes through as many rounds as you want, and you get some output. To decrypt it, you pick that up and you put it in the top and you run it again. And even if this F is a one-way hash function that can't be reversed, that still decrypts it. What?
Come on.
I mean, no, this is why I love Feistel ciphers. So we're just going to do it. We're going to start with L and R, and we're going to work through, and we'll see that it does actually reverse itself, right? Which is just amazing. I mean, maybe you've seen a Feistel cipher before, maybe you know this happens, right? But I think, when the first time I learned about this, I thought, that is awesome. So, let's do this. This is the left, this is the right. Now, for the sake of argument, they're the same size in this one. The right's going to come down here, and it's going to go through this function. So we're going to put in a key into this F, and it's a lot more secure to make these a sub-key, so lots of different keys for each round. So this is going to be key 1, this is going to be key 2, like this. This F is a round function that combines whatever comes in with the key and mixes it up and sends it out here. This R comes through this F, yeah, and it's XORed with this L. And this comes down to here. So this element is L XOR F with R and K1. So I mean that's going to look like gibberish as far as I'm concerned. This side is fairly straightforward. The R just comes straight down and turns into an R, like that. So let's do the next round. This is going to come down here and go through here, and then it's going to be XORed with this R. So this output here is R XOR F of this, which is L, I'm going to run out of space, L XOR F of R K1 of K2, like that. Is that right? I think it's right. Maybe it's a good thing that we didn't do 3 rounds or 4 rounds of this, because this could take me quite a while by hand. This one is going to get copied down, so this is going to be L XOR F of R and K1. Now both of these will look like gibberish. We're going to switch them around here. I won't draw them in quite yet, right? But this one comes down here and this one comes down here. Feel free to animate it, Sean.
Thanks for that.
Right. So now we're going to see how we can decrypt this back to L and R, and all we have to do is take this, put it in the top, and we have to swap our subkeys around because of course the rounds are happening in a different order. So I'm going to draw this exact same structure again on the next piece of paper so that we have something new to work on. Otherwise I'm going to get very confused. So this could be a competition. How fast can you draw a Feistel cipher from memory? I mean, they're not nearly wide enough for me to fit my stuff in. Alright, let's go again. I think that's right, you know. So the keys need to be in a different order. So this is going to be K2 coming in here, and this is going to be K1 coming in here. Reversing these keys, you know, algorithmically not too much of a problem. That will be a list of data or something like that. Very straightforward. Alright, so let's copy our data, our ciphertext in. We're sort of going to do do that and plug them in like this. Yeah. See what I'm doing? So I'm going to draw them in. So bear with me. This one is going to be over here. R XOR F of L XOR F R K1 K2.
Yeah.
And we'll just pretend that green line's a little bit further along. Right? And this one is just L XOR F of R K1. And then we're going to see what happens. Can you remember what it was that's really interesting about XOR if you do it again a second time?
It's the reversible thing, right? Isn't
It's
it?
the reversible thing.
Yeah.
Right? That's the key to this whole thing.
Yeah.
When you XOR something with the same thing again, it undoes it. Right? So what happens here of L F of R K1 K2, which is this bit. So that's going to come in XOR with this, and we're just going to get R out again here. This gets copied down here, so L XOR F of R K1. So let's go again. R comes in here, it becomes F of R K1, XOR with this, this becomes L, R gets passed down here, L goes to here, R goes to here.
Fixed size block of plain data into a block of ciphers data of equal size using a symmetric key. It is famous by Horst Feistel. The block ciphers are crucial for implementing function and then swaps the halves. This structure allows for complex encryption operations to be reversed reliably for decryption. So we have some kind of F function mixes the bits of halves the block with some kind of key material. The complexity of the F function affects the cipher's resistance to various attacks. Different implementations can use various cryptographic techniques within the F function to enhance security. So we have vast applications for the cryptographic hardware. Particular ciphers are fundamental in the design of hardware-based encryption devices due to their structured and predictable data processing patterns. The structure allows for easy implementation in hardware with a minimal number of logic gates, contributing to cost-effective and power-efficient design, which is very important in our real environment. Adjustable block sizes and the number of rounds make functional ciphers versatile for different levels of security requirements in the hardware implementation. The symmetric structure ensures that the encryption and decryption processes can be implemented with the same hardware logic, reducing complexity and resources usage. Hardware implementation can be tailored with specific functional functions and key schedules to enhance security against physical attacks such as side channel attacks. So we have applications in the blockchain technology, secure hardware wallets for cryptocurrencies. All of them are using block ciphers. Ongoing research into optimizing functional cipher implementations to enhance security features and reduce power consumption. So common issues and vulnerabilities, the vast range of this. There can be weak key schedules, simplistic or poorly designed key, can lead to predictable cryptographic weaknesses, sub-key repetition, and full injection attacks. So the real issue of ensuring safety and performance, resistance against differential and linear cryptanalysis by verifying algorithm properties and behaviors, ensuring that key schedule algorithms are robust against known vulnerabilities. We have to specify performance metrics, for example using clock cycles, such as time complexity and resource utilization. Minimal number of rounds needed to ensure security without compromising performance. So, as you can see, I have there are plenty of implementations of functional block ciphers, and I have chosen Magma implementation. So Magma block cipher, you can check this on Wikipedia, which is also called a Ghost. And let's check some kind of official specification PDF file on this. It's close to 4, and this called are permutations. This is a function between this ring and to this algebraic ring. So I have implemented this inside the Verilog. You can find this using some kind of sources. It's a Vivada project. Let's check the actual implementation of this. permutation inside the input we have 4-bit number, as the output we have 4-bit number. We have to specify those wires, and then here we are doing some connection with the MUX model inside the Verilog using some dot notation. Then we assign the outputs for this particular permutation. For wire 0 we have some kind of encoding for this one. For wire 15 we have some kind of encoding for this number. So as you can see, it's pretty simple. It is encoded in the hex notation. And here we have an AND model. We can try to visualize using the website which I showed previously. So let's begin. Load some sorry. Okay, full header, paste and run. Okay, we have to define the MUX, which is a part of our project. Okay, it in another way. Example code, browse, ICO2, magma, source, MUX. This one. There are a lot of dependencies for this project. Okay. Now we can see the permutation implementation for this model as a scheme. A digital electrical circuit. We have the output, those things. Okay. Now we are able to find the transitioning functions. So each function should be implemented in this way, so as we described in the standard. Now we have to implement this inside the Verilog. For example, t-transform function. How does it implement it? We can check this function is as input 32 bits word, output it's a 32-bit words. It's a concatenation symbol. It went through some kind of the permutation. It concatenates for 4 bits outputs for each permutation, and then we get the result, the output word. So as you can see, we have the input wire, output wire, as same as defined in the standard. Then we do some input and output wire, do some connections between our models from previous ones. We connect the wires from the previous models for permutations, for first, second, third, etc. And then we calculate the concatenation using some kind of assign notation. The output, this one. Now we are ready to implement this model. We do the same calculation for the G. This is a way how we can formulate our keys inside our logic. And this is the main encryption formula. This is the main encryption formula. And for example, we can implement this sequentially. As our input we get some kind of 32-bit word and another 32-bit word, and it goes to the first transform function, applied for the another one, and it calculated sequentially until we get the encrypted message. In total we have 32 rounds for this kind of algorithm. So the naive approach of doing the hardware we can just, okay, can we do it in just one cycle? Okay, we can put here just 32-bit word, another 32-bit word, do some calculation using our G-transform function, do some calculation of our keys directly from the G function, and get some output in just one cycle. It's not gonna work, because if we do this on some adequate frequency, there's some asynchronization of this device. So how can we do high speed data transfer for those kind of hardware? At the beginning, we have to implement some kind of register or just a lag operator. If we get some kind of data here, it's calculated for the our G-transform function. Then we have to wait one cycle, and then we are going to do some another encryption using this algorithm, and we do all the same things for just vector of our encryption data. And this is how we can output our hardware and get the encrypted message each cycle until we wait it goes through all of this. It works, but it's very expensive, because as you can see, we have a lot of modules which transforms here, and they are do the same. But sometimes we are trying to do some low-cost solution and minimize the area of the chip. This is the solution for Magma Cipher hardware. This is a minimal square area of a chip implementation. At the beginning, we have to implement, the idea is following. Instead of just copying this G-transform function, we implement only one G-transform function and universal bond. This is a mux operator, this is another mux operator for the keys. Each time we have to initiate the key, which key goes to this calculation. And this works well for every bit of information. And without start, this device shouldn't work. That's why as an input. This device I'm going to implement inside the Verilog and verify inside the ACL2. And in my repository, you can check the actual verification algorithm in the future. So, performance hardware using this schema. I think it will be a mistake just copy and paste this component. And there is a common approach to speed up chip performance. For example, if you need to get 3x acceleration in your computation, it will be preferable to just copy and paste the same model 3 times. But in a block cipher, you should know the core implementation of the logic inside a chip to decide which version of it is suitable to copy and which is not. So that's why I prefer to maximum performance computation this implementation of the hardware instead of this, because this goes slow. I implemented the slow version because it's easy to verify. So let's discuss step-by-step verification process using ACL2. Define the structure of the Feistel block cipher, including its rounds, Feistel function and key schedule in Verilog. Then clearly state using first-order logic expressions about the security and performance properties and the cipher needs to meet. This might include no leakage of plain information, resistance to specific cryptographic attacks, and efficiency metric like cycle counts. Create supported lemmas that might be needed to prove more complex theorems, breaking down the proofs into manageable parts. That's why we just formally verify some permutations embedded inside the Verilog, inside the ACL2. Sorry. For example, write ACL2 theorems that express the properties. Here's an example of how you might express the theorem for correctness for those kind of chips. We define the Magma correctness theorem. It's formulated as follows. If we have a valid key and if we have a valid plain text as a precondition, it's same as the ACL2. It should be encoded in predefined inside the Common Lisp rather than Verilog. And using SV expressions for the embedding Verilog for ACL2, we can validate this theorem using some kind of tactics from the SV book or just SV framework. Here's a basic structure for writing a proof that the encryption and decryption operations are inverse of each other. Assuming you have defined encrypt and decrypt functions using Verilog, and encrypt and decrypt functions using Common Lisp. Tedious to understand all of these parentheses, but the Lisp, Common Lisp language is very, very productive language if you are quite familiar with those techniques. So then we have theorems will assert that for all valid keys and data, the number of cycles taken by the encryption and decryption function should not exceed the defined limits. We are able to formally state performance metrics for our Verilog design. This is the logic clocks, which was firstly which famous by another theorist who invented some logic clocks with some concurrent systems. And here we can encrypt key data, define an amount of rounds, and using some kind of induction tactics, we can prove that this software, this hardware, satisfy this statement. Unlike simulation, which tests specific scenarios, SL2's theorem proving approach ensures coverage of all possible states and inputs, providing a more comprehensive verification. SL2 can identify subtle bugs that might not be triggered in typical test scenarios used in simulation, thereby reducing the risk of latent defects. For example, with some kind of physical invariant, which allows you to, for example, verify digital circuit with some kind of analog part. And those parts should be like a theorem. So it's pretty cool thing to emulate even physics inside the theorem prover. It is also possible. SL2 provides formal proof of correctness that guarantee the absence of certain types of errors under all possible conditions, rather than providing probabilistic assurance as seen in simulations. So SL2 uses rigorous mathematical methods to prove properties, offering a higher level of assurance that the system functions are correctly under its specification. SL2 can be used alongside Verilog to verify both the design and the implementation. The formal methods in SL2 can complement the Verilog simulation by covering aspects that are hard to simulate. SL2 is particularly useful for verifying the algorithms and core logic encoded in Verilog, ensuring that these critical components are error-free. So, for example, using some kind of induction, you can formally state that it goes well for every possible situation. Once the probability is proven in SL2, it does not need to be retested in future regression cycles unless the relevant specifications change. For example, in a common situation, we just do some model checking and simulation for one particular models. But if we combine those models with inside the circuit, we have some conditions where it's not be predictable via just one tested model. ACL2 allows to do some component analysis. It's just split the model, and the output will always be predictable even in the complex systems. SL2 generates documentation of proofs as a byproduct, which aids in maintaining the system and understanding the verification base over time. Theorem proofs in SL2 are scalable with increasing complexity, which is crucial for large and complex systems that are challenging to handle through simulation ones. For example, if inside the GPU or CPU, big large systems for the VLCI, we have a lot of components, a lot of hardware designs, and usually it is not even possible to simulate all of those complex systems using your even very, very high reliable and efficient hardware. That's why we have to use SL2 in some kind of very complex situation, and it is very scalable. Now we have some kind of trends and technology that allows you to use this kind of theorem proving technology in the next level. for example, integration with AI and machine learning, I would like to do research in this particular situation. As you can see, I'm thinking about this task. For example, if you are a user, you would like to automate all of the things inside the theorem proof. For example, do some Verilog tests, do some invariant generation, do some theorem proving, etc. You don't want to do it by hand. That's why you have to describe to some kind of generative AI. And this kind of generative AI, using some kind of tricks, should do the same job for you. And then you, as a user, have to verify the output is pretty satisfiable for you. And if you get the results, you are able to do some corrections and rewriting for your output results. So it will be explode in terms of productivity. And this is a quite new approach, and I hope it will be useful for real IT and hardware environments. And other things, it's improved user interface. As you can see, ACL2 ACL2 is just a read evaluation loop inside the terminal. It allows you to, for example, calculate some kind of lists, do some empty lists, do some theorem proving. Also, you are able to do something like this: open file and copy and paste inside your repo and check what's going on inside it. Then this goes to check all the proofs defined on those files, and then you are able to implement some kind of verification that I showed previously. And this is not quite user-friendly, and I think there is room for improvement for using, for example, a Scala user interface like in Isabelle, or some kind of VS Code automation to do this much more pretty for the end user. We can use those technologies for blockchain and cryptocurrencies, which is a pretty interesting topic because, for example, in the ACL2 you have smart contract models, some kind of the blockchain encryptions. All of them are quite useful for checking the smart contracts programs, and as I mentioned previously, there's a possibility to do some encryption and hardware design for Internet of Things security. We can do also as a book in ACL post-quantum cryptography. It is also implemented. It is already implemented inside the ACL2, and possibly do some homomorphic encryption algorithms, which has very large types of implications in our real world. So if you have any questions, please send me email or via message on the LinkedIn, and I will be more than happy to answer them. Thank you. Okay, any questions? Okay, so it's Feistel cipher encryption is just a common framework for many different types of ciphers. I have tried to describe the Magma block cipher, which is a part of the family of Feistel block ciphers. So the main idea of this, just we can do some encoding do some encoding, and those encodings will be the same as we can use the same hardware for decrypting using the reverse sequence of the keys. And for example, in Magma cipher, it's just a particular implementation of this idea. At first, we do some permutations. Those permutations are used by the transitioning function, which are implemented for each round. They're all the same for each round. And we have just a set of keys, which are formulated with concatenation. And this is a way how we can do encoding here. We just continuously do transitioning inside the G function is just this one, which is a part of the GK transition. GK transition is a part of T transition. T transition is just permutations, and permutations gets the inputs uncrypted, which do the encryption as an input. So first step, second step, third step, fourth step, fifth step, and we'll do all the same things every round. We can encrypt with K1, with the K2, with the K3, etc. 32 rounds, and in the end we get the output or as an encrypted message. And we do the same thing in the reverse order for decryption this, and the output will be the decrypted message. This is how it works. In this particular situation, it's defined as constants. Yeah. So, but the order of those keys are just opposite. Okay. For encryption, we can do from the first to the last, and for decrypt, we do from the last to the first. For some kind of algorithm, there is a possibility to do this, but there is just room for undefined behavior for those kind of ciphers, and we can't just formally prove that those kind of dynamic modulated keys are secure, and how are they stable for cryptanalysis. It's an open question. Yeah. Yeah. Yeah, that's why we should to specify the standard and not to go to go forward in another direction. Don't do any experiments, because possibly it can violate our cryptography. And the reason why do we need the Feistel cipher block cipher, we need to implement inside the hardware. It should be fast, easy to use, and cost effective. This is the reason why we should use the Verilog, some formal verification, etc. If we do some RSA, it's an asymmetric key, so it's just another types of cryptography algorithms. So it could be implemented for some kind of the transferring protocols algorithm when we're trying to secure our data through the channels. But block ciphers are symmetrical algorithms, and they usually do for example, for cryptographic encryption for the USB drivers, for something local hardware. They don't do some data transfer for far for the remote transferring data without any possibility to share the key. Okay, I recommend you to check those problems create the bus decoder plus FIFO model inside the Verilog burst, which is the key in the parameter for our hardware design. I will upload the implement of encryption modulation for Feistel cipher lately, and which is very useful technique. It's a universal register interface, which can be also implemented in Verilog, and generating a gray code sequence implement a very good start to begin your hardware designer career. Definition by a constant C, it's a models parameter. It's just we do some division under some ring. Round the number of individual bits in the input vector, return the result as a double number, and do the same addition of two numbers with saturation. If difficult, the output should be the maximum value. Calculate the most significant bit of a double number. The number can also be issued as a double number. So those problems are quite interesting to begin with, and it is also interesting to find the solution using SL2.